So good afternoon to all of you.
Good afternoon, sir.
Good afternoon. Okay, now yesterday we just spent some time on the Mathematica, some of the Mathematica course that we want to learn, particularly on the pure function. And then we just given a hint for numerical methods. And there is some question regarding the error analysis in the interpolation. Okay, so what I did here, one typical problem which I have taken, and then I have used, I'm going to use the error bound formula directly, because this derivation part you can always look into it. But I'm going to explain how to solve this or how to find the errors when there is error in your interpolation function. So I have taken a typical problem of e power 2x minus x. This is the function. And we have taken the points x is equal to 1, 1.25 and 1.6. And we wanted to find out the interpolation at 1.4 and also calculate the error in this interpolation of this data. Okay, what is the error which is involved? So we have already seen number of problems where we can find out the interpolation, but here we have the function itself is given, and we are going to generate the data at 3 different points, 1, 1.25 and 1.6. Okay, so generate them and do the interpolating polynomial using Mathematica code itself, or you can try with whatever I have described earlier that can be used and get the polynomial first. Okay, interpolating polynomial, which is, this is what your interpolating polynomial, and P2 can be used to find out the value of the x at 1.4. Okay, this is what your P2, find the value at, what is the value? X is equal to, substitute this is as a 1.4, I'll get the value. Okay, so this is good so far, fine. We are able to find out interpolating value for this because function is available and the value of x equal to 1.4 can be found because we are within this region of interpolating value of the x, because it is interpolated from 1 to 1.6. Okay, and you can go beyond, little beyond that also. Okay, now the error part is, this is f of n plus f1 xi of x, which means the bound value between this any one of this range. Okay, that's going to be your xi, which is the within that x is lying. And this is n plus 1 factorial with the x minus x0, x minus 1 and x minus n. This depends on the how many number of n that you are going to have. Okay, or the number of data points that will decide what could be the value of that. So now we take this f n plus 1 for this data is 3 data are there, therefore 2 polynomial interpolation is second order polynomial, therefore there are 3 data points that are available. So this should be this function, whatever I have to differentiate it 3 times. That's going to be f triple prime, which is equal to 8 into e power x, and this is also same as see here what's going to happen now. D of, take the function here and include it as a differential and make x 3 times. That's what the meaning of this. If I do that, I'll get the same thing again. So f triple prime is equivalent to d of e power x minus x. X is differentiated 3 times. Same thing will be. That I'll show you. Once you execute this, that will be known. So next step is, this has been found now. And what is the maximum value for that? Is for x is lying 1 to 1.6. If I take the substitute for 1.6, this is the number that will be getting it for the maximum value. Otherwise, you can find out this 8 into e power 2x maximum value by differentiating, then equating 0, and then substituting, because it's exponentially varying function. Therefore, directly one can find that x is equal to 1.6 can be substituted, and this is the number that you would be getting it, that I'm able to get it. Okay? F triple prime at x equal to 1.6. For this 1.6 the maximum value, this range. Okay, and that is going to be the maximum range one for this value. Next, the maximum of this x minus x0, x minus x1, that also should be found parallelly. You can see that can be found. This is what the maximum for this range 1 to 1.6. That is the number that has been given. This number determination is going to be little tricky, that you should be doing little carefully. So what you have to do, d of x minus 1, x minus 1.2, and that I am differentiating this. Okay, it should be differentiated. Once I differentiate, I have this is the solution which I have. Now I wanted to find out what is the maximum of this function, which means at what value of x that has a maximum value that can be found, and that can be substituted with the ABS value of x minus 1, x minus 1.2, x minus 1.6. This is the value at which that is happening. That happens to be this number. That is the maximum of this x minus 1, x minus 1.2, x minus 2, the range of x comma 1.6. Which this can be checked here by plotting the function. So you can see here, this is the maximum it reaches within the range. Of course, this has been ignored, which is still I don't have the answer, but this is the number which has been taken for this calculation. This I have not substituted and found, but there is this number has been, whatever it has been given here, 0.0075464, this is the maximum that has been shown. Okay, that is being picked up from here. You can see this function is a maximum around that point. Okay, so maybe you can get the coordinates and see that this is 7.75 and 0.075. That is it. This is the number which I'm able to locate here. That number is used. Maybe part of it comes in this range first. That first maximum has been taken. There is another maximum also, but it has been taken. First maximum that has been taken. Another maximum is somewhere here. Okay, but this maximum only considered, which I don't know what is the reason for it. But anyway, this is the number that has been found. That number is this. Okay, so get this number, and we know this number we are able to find out by the maximizing this. This also has been found maximizing that. You have left with only the factorial part. Okay, that is 3 factorial, which is equal to 6. Substitute that. This is the error that you will be getting it. This is a bound error. Error bound is this much, and actual error bound for the function as it is f 1.4. What is the f which we have defined here is this number, this function. So f 2.7 has been, or 1.4 has been found, minus interpolated data p2 of this 1.4. This is the difference, and this is the number that you are getting it, and the actual error is less than or equal to that is being satisfied. This is what your actual formula that is being satisfied here. So here are some of the important points that should be noted. So I understood there is some understanding I have right now. Why you have the difficulty in finding the error bounds? Because you have to think about the derivative component here to find the maximum of these functions. Okay, find out them, and appropriately that should be substituted only. You can get the results of error bound over the region. There is a error which is bound within that region of xi of x. There is certain region of x. Okay, for the corresponding xi, there's going to be an error. So that is the error bound. Okay, that is being evaluated by using this expression. And probably you can try for this data 4, which is calculated here. See, because data 4 is what? Log function. Yeah. This is the data 2.53 ln of x. That's the data. And this is the data which we have. So suppose if the data alone is given, this function form which you do not know, then it's difficult for us to calculate the error bound because we do not know the actual function to find the derivative of that. So therefore, it is only data is available. Then it's difficult for me for us to find out because you need to have the function. Okay, and then this of course is available, but this you need to have a function. So in this case, ln of action is given. Therefore, you can find out and make sure that it is coming less than or equal to this value that has been found, like what is being explained here. So that is how the error should be looked into it and analyzed. And what is the idea here to find the maximum? For example, this is what the function which I have plotted. Correct? And for this, we are finding the maximum. X minus 1, x minus 1.2, x minus 1. So when I plot this, I have a function here. Then, well, you can differentiate it and equal to 0, solve that, we'll get the point. Substitute those points into this, that is going to be your number. Okay? You remember that? Do you remember how to find the maximum of the given function? It's supposed to be exactly 0 because there is an error, there is error bound that gives a finite value. You get the point?
Yes, sir.
So there is it's supposed to be 0, but there is an error which is involved in this polynomial interpolation. That error component is reflected by that process. Because you are differentiating with respect to this, any given function. For example, that is I have a function, I have taken it, I plotted it. And at this point, what happened to the slope? Goes to 0. What point it goes to 0? Corresponding magnitude that has been found. That's what has been done here. I hope it's clear for you. I'm plotting this ABS value of x minus 1, x minus 1.2, x minus 1.3. Maybe this ABS value, if you look at it, might be a negative one. That positive must have been taken. That's also possible. Why this has not been considered? Maybe if I remove it and plot it, and I can probably see that, yeah, I think positive value has been taken, negative has been ignored for the maximum. So you take this ABS, plot it. This is for the actual curve that I have. Now, where is the maximum? How do I find out? Maximize this function. How do I find it? I can find by, what am I supposed to do? Take a differential of this, which means at the point somewhere it goes to 0. Okay, so where the differential here? This here. This is the differential of that. Okay, equal to 0, and I am getting the point 1.10933. You can see the 1.10993 somewhere here. At that point, the slope goes to 0. Is that right? That's the maximum value that has been picked out by this process. I hope it's clear.
Yes, sir.
So that's the idea here. So these are the things that one has to do when you find out the error bound. And also you should know the function. That is the reason why we have a little complicated for estimating the errors. So this function also should be known to us. And you should be in a position to find out what is the maximum which is lying, substitute and get the numbers, put it back into your calculation and confirm it. Yes, this is what the actual value, and it is less than or equal to this numbers. That's what the idea in the error calculation. You tried this, already I tried, and we are getting this number close to that. That's satisfying also, less than or equal to bound. And I've just given this here, but you can make an effort to find out that. Not a big thing. Same procedure you follow. Exactly same procedure follow. Only thing the function here is now, instead of e power 2x minus x, you have a ln of x. That's all. Find out the error, and that error also false. Quite good. Whatever is described here, that is happening. Just repeat, confirm it, and make sure that yes, seems to be. This formula seems to be consistent for the error bound. That can be confirmed. If you try for other data, since you do not know the function, it is difficult to find out difficult to find out the error that's involved. You need to have the function. For example, in this problem, this is something like a number that has been found, no? Is equal to some functional form is there. Then if you have that functional form, that function can be used and differentiated the number of times that is required, and then use the number of data points corresponding to that. That also you maximize it and put them together and see that that is getting matched with that, and you are getting the error which you get. Okay. Try some of the problems where functions are available, follow the same methods, then find out the error. And also please note that it's supposed to be this determination of maximum value is supposed to be exact, but these are all, you are following a polynomial approximation, there is going to be an error that's involved, that we are able to pick it up. That errors are picked up. That is why you are giving a region in which this is bound, error bound, which we give it for a particular region. Between 1 to 1.2, you find this is going to be error bound. Okay, and xi, what we refer here is something like 1 to 1.2, 1.3. Okay, in this range, the maximum error is less than or equal to this. That's what it means. I hope it's clear now. You can jump to the next part of it, which is numerical integration. This I will send to you people after some time and have a look at it. So numerical integration is the first step. What you have to do, find out the area under the curve. How do I find out the area under the curve? Make it a small rectangles. Okay, as many number of rectangles as possible, and try to see that the rectangle, this portion getting minimized. This is the area under the curve. That is the integration of this result between 0 to 2. And what is this function which I have given here? The square root of 1 plus x square. So between 0 to 2, 1 plus x square root, if I plot, this is the curve that I am getting it. So if I integrate that from 0 to 2, from here to here, I will be getting this area under this curve. So one simplest possible thing is, as a rectangle means, find out x, find out y, multiply them. That is the first one. Find out x, find out y, multiply them. That is the second one. Third, fourth, 5, 6, go on. And see that this portion is getting reduced by taking large number of points, which means this del x, or the x-axis part, you make it as small as possible so that this will be the component what has been left out will be minimum. That is possible for us to do it by selecting the number of rectangles that you want. That can be fixed by taking b minus a divided by n. So your n will tell you how small is the box is. Okay. So 0 to 2, n is 20 now, which I have taken delta x. That is being fixed. Okay. So what you have to do, we need to have a rectangle now. Rectangle should be there and the area of the rectangle should be found. And you can see this is your y of the rectangle, and this is the x of the rectangle. The y is nothing but with respect to the function. Put this x into your function. Okay. With this amount of del x starting from a and I into del x, I varies 1, 2, 3, 4. Each time I will get a y and this is x. And rectangle y is, which means you know the length and breadth of the rectangle every time. That's all. That is the idea throughout. Entire integration concept is based on this. And you just improve it for the functions and the various mathematical approaches that are available, you develop them, and then that will become a different methods. So now the basic idea is to find out what is the rectangles and find the area of the rectangles. And y-axis is with the function. X-axis is the delta x, which is done by this. That's all. Okay, let's take this and see what is happening now with respect to this number of points. And then what is the expected actual value, and after making it with this kind of rectangles, and what is the total area, and the difference between them is going to be an error that's involved, and that error, how do we minimize it, and what is the other techniques that are available that can also be seen. You can see here, this is moving to the right, or you can say these boxes are there, this touching the curve to the left. Box, the edge is, this edge, first edge is cutting to the left. And I can make a calculation making it a touch on the right side, which means I will make a curve that can pass through these lines. Okay, that's also possible. Right, it is the, now what we have done here is the left edges are joined. I can join the right edges also, or I can make it to pass through the middle of that. This point can be selected in the middle, which means the point of selection for the y will tell you whether we are going to have the so-called the left edge or a right edge or middle point. Is that right? So I have an x del s. The way I select, which now we find, this is having a, you can see this, for this box it's a left edge. This box is left edge, left edge, left edge. I can also make this to pass through this right edges. Okay, that's also possible. Or I can select middle of that. This I know, divide by 2 middle. This I know, this one middle by, divide by 2 middle. That also possible. Then do the summation. And you find there is some, there will be certain kind of an improvement that you would see when you go from left to left and to the right and to the midpoint. So summation can be taken about considering the left edges and right edges and then midpoint also. So now as it is the left edges, you look at the boxes, the left edges, when you go towards this y-axis, these are the left edges. Okay, so now this is the idea here, and we are showing these rectangles by making a plot of the rectangles so that it can be explicitly seen. Not just giving a numerical alone, visibly we want to see how this is happening. That is being done by taking the data points, take the data points and pick the points as rectangles. These are the values that's supposed to be there. Is that if I make a line, then I'll get a rectangle. That's what. This is a graphic object. It's like a line is a graphic object. Yesterday we have seen them. Circle we have seen. Disk is available. Line is also a graphic object. So line can also be made. And that line has been selected coordinates each time when I go from one box to other box. See, if I move the high values, it goes one box to the other box. That box also has been plotted here. That's the idea. This is the actual techniques to show graphically these efforts we are taking it, which we are plotting it. We go through the points, then make a plot of the function along with this, and then look at the things. Then you can see both together, and this is what the thing that's going to happen. Suppose if you change the n value, then you find that I can have a 10 points, 15 points, 20, 25, 30, 35, and then whether it's improving or not, that can also be checked. Okay, so that option is available now for you to check whether n has an effect or not. Definitely n will have an effect that can be calculated. Or error also can be calculated. We know what is the calculated value and the actual value. Okay, so look at this now. With this, the plot, the number of boxes. So what is expected now? We will be having something like 20 boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 boxes. Sum, that is the area. So approximate area is this, and the actual area is this. There is a difference. This is 1 square root of 1 plus x square root of y. You copy and paste, go to the other function. You don't have to do anything. Right? You follow what I'm saying? The whole thing has been available to you. You just copy and paste, change the function. What is the change here? Suppose f of x is 2 pi x. If I integrate this, what do I get? What is the integration of 2 pi x? Idea?
Pi x
Pi
square.
r square.
It is a circle. An equation of a circle pi r square that we will be getting it. So I have a straight line that is being used here. Find out this area. Because the function is straight line, is it not? Right? Come on. If I plot the function as it is, it's a straight line. Correct?
Yes, sir.
Yes,
Pi
sir.
x. But its area under that curve is equal to the area of this circle. Because 2 pi x dx is going to be pi x square. 0 to 3 is the range. And what you get is the value of the quantity what you have is going to be a circle that can be obtained now. Okay, now we have a straight line and area under the curve is going to be circle of radius 0 to 3 means 3 is the radius. Okay, this is 2 pi x square. Yes, is the radius. So now you can find out actual value can be found and what will be the difference that can also be cross-checked. So this is the actual value and this is the one which we have done it by summing up, taking the left edges. Okay, this is the left edges. Fine. So maybe if you wanted to have a little more detailed way, what is this? Where is the parameter which is available that can be changed? Now I'll make it as a something like 30 now. Let me make it, see what's happening. Okay, let me first do this with the 20 and confirm with skin properly. It should work, there should not be any problem. But the first input, second one, there this is the plotting it, and the area is given, and you can find out the difference between. Suppose this number, you just make note of this 2.89683. If I make it 30, what would you expect? What would you expect? Oh. Now, if you count how many will be there, 30 will be there. Now it is improved. We are going towards the actual value, right? Which means this error contribution getting reduced if I go for the number of boxes which are closely spaced. And that error component goes down. Suppose now I make it 50 now. Yeah, see here. Very, very minute contributions here. 2.933 is 2.9. This is second decimal even. This is also high. Okay. Now, yes, you will take what matter is 2.9 is almost 2.9. This is the number of boxes that being added, and you can see that is almost you are having a results close to somewhere about second decimal accuracy. Is it not? And 9.5 this 9.49 it can be taken. So you have a 2 decimal accuracy, but 3 dimensional accuracy is not possible. Okay. And then a class method. Okay. So now you can see that number of data points or the number of rectangles that you are going to change, then that's going to contribute to the more by reducing the error. Okay. This is another way to take it. So the difference of x7. So this is so much of area has been left out in the calculation. Okay. So therefore this error becomes large. But same thing you can try here also by changing the number. Yes, here it has taken already 40, and this is 27.56, and the actual value is 28 point. This is also too much now. Okay, for the data points, 40, even for the 40 data points, the error is rather high. Okay, second digit error is here. So suppose if I make a larger number, then probably you will see that's going to be much better now. Okay, the result which is now 28.133. So now only we started coming close to 28.27. Even only 2 digits only we are having. Okay, so probably this requires much more number of steps than this one, because this is a curve surface, which is a straight line. Therefore, that shape also matters here. You can see they are going to be quite high here. Okay, which means depending on the nature of the function, number of iterations also get changes when you do simple rectangular summations. Okay, so this is how much is 20? This is 26.86, and you can clearly feel each one of them makes a contribution. Because a straight line and each one almost equally makes the contribution, is it not? Because this size is fixed, and this is a triangle which is not included, and every one of the point you have to take. That's going to be the contribution of your error. So these are all taken care of by algebraically by fixing over the ranges. Over this range, this is bound. This is bound error only. We are trying to make it give the results. That's why you write it as less than or equal. We do not know exactly how much is the error, but within that bound, how much is the error possible, that is the result which we have given in the previous case. Similarly, this is going to happen here also. I hope it's clear what I'm trying to explain here. So if you make it smaller and smaller, the error is going to be smaller, and this bound error that can be shown with the z of x a given. But for this, you can see everywhere there's going to be equal contribution. This is the case. Okay, then you can say that for the small bound values of x, whatever the error that is there, that should be contributed. That should be added up for all of them. So that's going to be the total error. Okay, so now this is the basic idea of the integration is described here, and here is the idea of the so-called. You know what is this one? What is the test been done? Can you guess what could be this program here? And this we are clearing all AF, GH, MX, whatever has been used. We are trying to do something here. Here we are finding out the area, and here we are trying to do something else on this f of x square, f of x. Okay, so just tell me what could be this one. In the limit of x goes to 0, going to be a derivative. For this function, we are going to see the derivative. You look at how the derivative is going to be there and find out for different values of h and make the h take it to almost close to 0. Look at this. So here is the area under the curve. Here it is the limit which is going to take it to the finding the differentiation of a given function at a given point. Okay. So now half x square, we are writing it m of h underscore with this functional form, taking a value a plus h plus f of a divided by h, and make the h as small as possible. So g of x is equal to m of h x minus a plus f of a, which means this function with the difference of x minus a multiplied and take the mh, that is going to be your derivative function g of x. Okay, we are going to plot x of x and g of x, and when the h goes to smaller and smaller, see what is going to happen. You can visually see what is that we are trying to do with the numbers which we are getting it. So the blue line, you are trying to locate it for a given point. As h, the limit goes to 0, it should go and touch this point somewhere. Okay, you're able to see that there is a curve here. This red one is the first f of x, which is half x square. Okay, and here is the g of x, which we are evaluating for different values of h by using this, the differentiation which we try to see for a small x plus del x, what is going to change the y plus del y. That is what this relation, and make the h different values. So that has been done by 2 power of I minus 1. If I take I larger and larger, this magnitude becomes smaller and smaller. So correspondingly, the h will be substituted here. Manipulate h with this. Follow? H of we are going up to 4. 2 power I minus 4. So what happened to this power I minus 3, which is going to be vary, and it reduces your h value as we go along with the higher value of I. Okay, that is being taken care into your functions here, and that is being used here for m of h. That is being incorporated in your plot. The idea, very simple idea. Manipulate this with these functions that goes into this. We are going to see the result now. Now you change the h. Now we can put the control placement. Make it on the top so that you can see the calculator. Okay, so this is what the graph which you have. To start with, h is equal to, how much is the h? I equal to 0, so h is equal to 2. With that h is equal to, if I evaluate this, this is what the blue line that I am getting it, that is your g of x. Is it clear for all of you? mh underscore of this,
Yes,
that is being used here to get the g of x. So that's going to be the slope line. If I reduce the, if I increase the I, h magnitude goes down. Very nicely you can see. And at particular point, it is going to be h in the limit goes to 0. That is going to be the slope at that point. This is what it is. If you want to go further, you just put 10 power 8 or so, and then make a change. Still, it goes to the precisely to the smallest possible number. And this is what the number. Okay, then it's 8. And see, 8 means you have a 2 power minus 7. That's the number. Am I right? So, clear for you. This is the number that's fine. Not 7, 8, 1, 2, 5 is the magnitude of the h at the end. I minus 1, this is 8, 7, 2 power minus 1, because this is a minus sign here. And as you change the I value, the magnitude of h becomes smaller and smaller. I think it's clear for all of you. I'm just making it smaller and smaller. And when it becomes bigger and bigger, you can see it's going to pass through this curve. And I'm locating it by making it smaller and smaller. And this is the visualization of this so-called integration. This is the visualization of the, I'm sorry, this is visualization, the differentiation, this is visualization, integration. This is what the basic concept involved for this, any of the given function. This is what you'll be trying to do. And every function has its own differential form and the integral form. And these two are get connected, integration and differentiation. Both are strongly linked. Okay. Is it clear for all of you now? I hope this is clear. This is what fantastically one can feel that yes, this is really differentiation. H goes to smaller and smaller. H tends to the limit of h goes to 0. That's what the derivative this point. That is what we try to do when I explain this acceleration, displacement, velocity, and accelerations. The connections. Slopes has been shown on this curve. So now you know what is the slope of this. Is that? What is slope of half x square? Come on, it's x, no? It's a straight line. It's passing through the origin. That's not going to happen. But we are finding out at this point. Okay. So therefore, at this point, whatever is here, that is the number that you will be getting it. Okay. If I take a derivative of this, I'm going to get a straight line that's going to be passing through the origin itself. Supposed to pass through origin. I'm taking different points, and if you take all the points together and then make a plot, this is at one point magnitude I know. Go to the second point, third point, fourth point. All of them you take it and make a plot of that will pass through. That is nothing but your. This is what your slope is. It's another line which is passing through that. This line, slope of this curve, we make it as blue and make it as green. And well, I have to put it in me. So my bracket should be there. This is, oh yeah, independently you have to make it. Show that independently three different curves close. It's the green line, you see? Which means if I find the magnitude of the slope at this point, that goes and sits on this point. That's what it means, vertically up. Okay? You get the point? Yes.
Yes, sir.
That magnitude is sitting on this. And that is how we will go to the next point, next point, next point. And if you combine them, that the green line will be automatically. Okay? That's the meaning of that. So, okay, I'll keep this also. Green can be kept, which is the slope as it is with the differential method. What we have, if you follow that, we will end up with this. For this function, it's going to be x. This is the results that you have. Okay. So, it's fine for us now to start with. And we will go to the some of them. Mathematical ground behind this left, right, and see left end point, right end point, or mid point. See the pictures here, representation. This is the left hand which we have seen. Visualization of numerical integration. This is the f of x is going like this. There to be these different points. X1, x2, x3. And this is another method where you are going to right hand of this. So right hand, left hand. And this is the midpoint. And what is the formula for doing that is very simple. Sum over I equal to I equal to 1 to n. Put the star xi star, f of xi star, xi minus xi minus 1. You are putting in a combined form in which your left hand means you use the starting. This f of xi should be x of I minus 1, so that it will be left end point. Okay? Please note this. This is important for you. Okay? So it's clear for you? When you come to the right, this is called the Riemann sum. Riemann has been proposed at the beginning. So when it comes to the other one, second one, right sum, you see xi star equal to xi itself. So this comes first in this case. This is coming to this case. And middle, you take xi plus xi minus 1 divided by 2. That is what the midpoint average. So this is the middle Riemann sum for all i's. And this is the number of points that are possible that will be divided, that will be decided by the number n for their bound region of A to B. So B minus A divided by. So this is what the whole thing which has been described with all possible numerical methods. We have one other thing which we have discussed, this left hand part which we have discussed, and you can convert into the right hand by using this initial value. And middle, you can do this by. So what I suggest is that what I am given in the exercise here, it's a left sum, left Riemann sum. You convert into that same program by right Riemann sum and the middle Riemann sum by making this chain, replacing the initial value for this function with the xi star. And this is same. That's all. Okay, you do that. This is del x. which means this is the delta x along the x-axis part of it, and this is y part of it. Y part you are making a small changes when you go for a left, right, and middle. That's all. That is the idea behind the numerical method for the integration by the rectangular part which we are. Okay. I hope this is clear for all of you, and we can make an effort in converting the whatever which I have described or given for this second part and the third one. By a small change, you just this alone you have to make a change. Okay, you have a trapezoid method which you already studied. Okay, see, these are the 15-point trapezoidal for a given function. If you count these lines, that's going to be 15 such line will be there. This is the curve which is shown here. And what is the method and what is the formula here for the trapezoidal is you have again similar to this b minus n 0.5, with of course half of that has been taken. You have the initial value and the end value, and then the remaining will be multiplied with the 2 corresponding to the number of points. Okay, let's say there's nothing great here. y0, y1 is the initial and the end point, and in between the points of y0 and yn, whatever you have multiplied by the 2 times yn, each one of them up to 2n minus 1. Then this b minus a divided by n divided by 2 is 0.5. That is what your common factor is. So this has been followed certain calculus approach and has been derived. And this expression is given by trapezoidal. And this, of course, you are already familiar, and we can go through them and get the idea about how to get this expression and understand this expression and make an implementation through Mathematica by, in fact, this is little modified by changing this. Sorry. Leave the initial and end point. All others are multiplied by 2. Okay. And the outside factor is this. b minus a divided by n into half. That's all. Once you have this idea, this seems to be also better. It's improved and it reduces the number of data points. Okay. And depending on the nature of the curve, you have to select this or this or this. Suppose completely fluctuating or oscillating are there, then sometimes midpoint will be by much better than the trapezoidal. So these are all analysis that one should be carried out by depending on the nature of the function which you are going to integrate. Okay. Here is the Simpson rule, 8-point Simpson. There are the 8 different points that's been taken here. And again, one-third rule which is y0 and yn will be there. You can see y1, y3, okay, y5. These are all multiplied by the factor 4, right? And even ones, y2 and y4 and y6, all are multiplied by the factor of 2. Again, this is a simple form where you have to group them in terms of the y0 and n, you leave it as substitute as it is. And when you have a second y0 to y1 is the second point. When it comes to y1, that should be multiplied by 4. Similarly, y3 is by 4. Then y5 by 4, y7 by 4. Then you have a y2 by 2, y4 by 2, y6 by 2. So this is a common factor. You can group them. And this is another way also you can write it. You can see there are 2 y2s by writing like this. Possible to rewrite it and then put it in the form you like. So either way you can do it, and it's going to be the Simpson rule. And some calculus approach has been used, and this has some advantage over the other methods that you have. And it is rather easy to implement it. Just put the function should be there and put the sum over it and take these factors properly, then you would be in a position to do it. So here is the nice demo to show all the 3 or 4, how much is the 5 different methods at a time for a different functions. Not only that, you are plotting the boxes also to show this, how many points contribute, how much is the value. So you have the functions of this type. You can add some more function or replace some more function. Okay. Then you have the method left sum, right sum, midpoint, trapezoid, and Simpson. Here is the simple curve or a simple program that has been done by manipulating this. So get all the numbers. Piecewise plot is also same as this, making it a box. These are all the additional things that are available under the manipulate, which you are already describing it, and then vary the parameters and select the function which you like, then try to demonstrate it. And probably you can see this one by one, we can see, visualize and see what are the technique which you have learned that can be clearly understandable. So now we can see 4 points with the left sum. Look at the error, this is available now. This is the approximate value which has been calculated for this curve. What is the curve? E power minus 2x. This is the curve. And how many points has been selected now? This is left sum. 4 point has been selected. This is the left sum. Left edge of the boxes has been connected here. 1, 2, 3, 4 areas. So you can see the number of. This is our excess added. So therefore the error is more. In this, you can increase the number of sub-interval as I have already indicated. The program, you can see the consequence of adding the number of data points. So the error goes down, already reached to 10 power minus 2, minus 10 to minus 2. The number of points has been taken. 12. Go ahead. Go ahead. Go ahead. And you see, proportionately that contribution will be varying also, depending on the function. Box sizes are equal, but the area contribution for the error will be more, and that it gets reduces when the magnitude is going down. So these are all the things that should be considered when you take the error bounds. Okay, it's not uniform every places. Depending on the curve, it changes. For example, at this, for this proportionately, maybe this is high. The small area, but it's this corresponding error is there. So this all should be taken in the error analysis. That's why error analysis becomes a little complex when you try to do this error analysis in this kind of integrations. Okay, this is for one type of a function. And come back to the 4 number of points again. So we'll take 4 or 5. Okay, 10 is here. If I do right sum, so the error will be, you can compare, make a comparison, right sum to the left sum and see what's happening. So it will become a right sum, now only become right sign, right sum. This is left sum, it takes a little bit of time because there are so many things have been put together. Computationally, it takes little time. Yes, from left, we are coming to the right sum. See the difference? Yes, come back. So this is the error contribution. Let me try to see whether the error is same. 9.16 10 minus 2. Okay. 9.16 10 minus 2. Is that same? Yeah. A little difference is there. Some, I think I have been in a hurry. So this is actually the left sum error is 1.05 into 10 power minus 1 for the same number of data sets. If I go to the right sum, it will be different. This is different, and this difference also should be efficient to accommodate them because the starting points are different, and each time that you are, what I'm trying to say, will be different. That makes the difference. Okay, and the f of xi for every time, for every point, that brings the difference. So that is why you feel that there is going to be appears to be same, but actually that's going to be different. That is reflected in the error component that you have. Okay, so now the same 10 points, midpoint, if you do it, what happens? What happened? The better side or much better, nah? It's improved.
Error has reduced
Come
considerably.
down, reduce considerably, it is reduced because half half of the previous one it must be, or even more than that. Is it not? Because this, for everywhere you find there's only a small bit. Okay, small bits are there. This is included here now. You follow? The area calculation, this portion is included by shifting to a midpoint. This is included. This is outside, this is excluded, but this is part of the curve that's included. So there is a portion which has been left out in the previous has been added here. Therefore, there is an improvement over the error in the midpoint calculation. And that, of course, it will be much. The same thing happened with respect to the increasing number of points also for the given right sum and left sum. If I make it 20, 32 is here, and I can make it 20. And look at this error what you have here. This 10 to the minus 4, 8.17 10 to the minus 4. This is minus 2. And this again, that sum is 8.07 10 to the minus 2. So this is how we look at things. Okay, so same 10 points. You take a trapezoidal method and a Simpson, and you can make a comparison. This is trapezoidal. Yeah, much better than the previous two methods. And for the Simpson, same thing. Look at this 6.8 10 to the minus 5. The trapezoidal, it will be whatever, 10 to the minus 3, minus 5, minus 3. These are the differences. This is where your calculus and the idea. See, if I look at carefully this one, it is sort of a combination of this left, right, and mid sum. That's how it looks. And weight factors also getting changes little bit. Weight factors also modifies. So therefore, you would see that the calculus approach based on these weight factors, then the method becomes more efficient. Yeah.
If subintervals is more, what will happen to errors?
What will happen?
Sir, here, sir.
Summing large number of left sum.
Subintervals.
Okay. You can take the number of data points in the left sum and right sum and mid sum. Is that not?
Yes, sir.
Okay, this is your left sum. Not trapezoid. This is left sum now. It's calculating. See, number of data points when it is going up, the error will come down. If, for example, let's take only one method. For example, left sum alone. I start from 10 points for the computation. It's going on now. It's computing and see, look at this 1.0 to 10 to the minus 1. Same thing if I make it 20. Please note down this number. You can have an idea about this number 1.0 10 to the minus, which means 0.105. That is your error. Now, if I make this equal to 20 for the same method,
Sir, your mic is muted.
Sir, connection പോകുന്നു തോന്നുന്നു.
Okay, I will call him.
Okay, sir.
I think we will wait for 2-3 minutes. Sometimes he would be restarting his machine. Okay.
Okay, sir. Sir, ഇപ്പോ നമുക്ക് കാണിച്ചു തന്നില്ലായിരുന്നോ സർ ഷൈൻ സർ?
Yes, പറയൂ.
അവിടെ സബ് ഇന്റർവെൽസ് ഒരുപാട് കൂട്ടുകയാണെങ്കിൽ ഓരോ മെത്തേഡിലും ഉണ്ടാവുന്ന ഡിഫറൻസ് ഇല്ലേ എറേഴ്സിലുള്ള അതില് ഇപ്പം സബ് ഇന്റർവെൽസ് കുറയുമ്പോൾ നല്ല വേരിയേഷൻ ഉണ്ടല്ലോ.
സബ് ഇന്റർവെൽസ് കുറയുമ്പോൾ
സ്വാഭാവികമായിട്ടും
വിളിക്കുന്നു.
ഓക്കെ സർ.
ഹലോ സർ. ബേസിക്കലി സബ് ഇന്റർവെല് പിന്നെ ഇന്റർവെല് കൂടിക്കഴിഞ്ഞാൽ കൂടുതൽ അപ്പോഴേ എറർ സ്വാഭാവികമായിട്ട് കുറയും. കാരണം എന്താ വെച്ചാല് പിന്നെ ഓക്കെ.
Is it okay? You are audible?
Yes, sir.
Something happening now. My net breaking in between. Okay, it doesn't matter. So now you can clearly feel that there is going to be a huge difference in terms of the same number of iterations.
Sir, screen is not sharing.
Screen you are not able to see?
No.
No, sir.
Okay, we'll check it now. Again, it's so screen seems to be all right for me. No screen now?
No, sir.
No, sir.
Okay, I'll start. Probably I have to start again and come back to you. Yeah, I'll do that. I'll try here. Close. I'll close and come back again. Okay?
Yes, sir.
Or you can repeat again entire screen one more time. Share. Okay, I hope it will be coming. Is it coming now?
Yeah, now slowly coming. Yeah, now it's coming.
Yeah.
That's right. So I think there is a red light is gone. Again, there's the green light has come back again. Okay. So you can feel that for a given number of points, okay, you can see the accuracy which is going to be enormous amount. For example, this is 10 to the minus 7. Same thing if I try to do with the trapezoid, then for 3 orders of difference already. Midpoint and the trapezoid are close. Okay, seems to be close by. (4.0 10 to the minus 4 for a given number of data points trapezoid, and go to the midpoint. This is same order 10 to the minus 4, but it is now higher. In fact, trapezoid midpoint seems to be better than trapezoid, because this is 2.04 in 10 to the minus 4. The trapezoid, it is 4.09 in 10 to the minus 4. So now there is a sort of competition between these two. Okay, and come to this right sum. And see, now this is about 5 orders of difference when compared to the Simpson to the right sum for the same number of data points. Now go to left sum. Again, about 5 orders of differences. That's why they're all very superior methods. But again, Simpson also has limitations, because when there is a fluctuating functions are there, then you should be very careful about the usage of the Simpson also. There are limitations. Doesn't mean that all will work out with the same kind of an accuracy. Very much depends on the nature of the function that really matters, and the number of data points, the number of points which you consider, that also has an influence on the accuracy. So I hope this is so clear here now with this kind of computation, that we are in a position to understand that area under the curve can be determined with the accuracy limitation depending on the method that you are going to adopt. and the number of data points. Now, I think for our computational limitations in terms of computational time, even a laptop is enough for you to do reasonably good computations for the determination of the area or the integrations for certain functions like what you are seeing here. Now, suppose if I go for a function of the type sin x, again, this depends on the nature of the function. As I said, you can see that this is the, how much is the data? 40 data points left sum. 2 power 2.3 into 10 power minus 2. Go ahead with the right sum. Same data point. 2.23, 2.24, not much difference. 2.24, 2.3. Midpoint should improve. 2 orders jump. Quite good compared to the other two. Trapezoid with the 40 and from minus 1. If you follow the Simpson, this limitation. That's fantastic. Much higher because your integration region you have what is that you have gone up to 0 to 2, the integration region, see 0 to 2 and x dx. Maybe if you try to do with suppose if it is fast varying, which means I have within the two I have a large number of waves that are there, then you look at the integration, you know how much difficulty that you have. You follow what I'm trying to say? Within the 0 to 2 I have a multiple number of waves, no? I just put say 5 times, 10 times. It might be huge. And you look at this same Simpson rule with the number of iterations, then you would see the real difficulty. Okay, then you have to look for alternate methods. I think you understand what I'm trying to explain. You just, if you have a 3 times, 4 times, 5 times, within the region of 0 to 2, I can have a more number of waves, multiple waves. Then you try to integrate, then you should be careful about the number of points that you are going to select. Any method for that matter. So those things should be natural process that you have to think. Then do it. Because now you are calculating up to 2, no, you are not even completed one cycle. Then integration will be much better. That's the reason why you have this accuracy of this much. The result is how much? Oh, that's again 3 orders of difference between the trapezoid and Simpson. Okay, next function. Of course, this is straight line, no issue at all. We are having exact, huh? Exact result is what? See, Simpson, even trapezoid is exact. Simpson is exact. See, we are able to feel the nature of the function has an influence in determining the error. Is it not? This is little error, left sum. This is lower, this is higher. That's because of the initial, the FF point what you select, that matters. Exact, this is, so even 40 with the straight line portion, there is going to be an error of the second decimal. Okay, even left sum, right sum also having one higher, this is one lower point. Midpoint is almost same. So actually what is happening, addition and excess are there, and there is a lower portion also there, but when it averages out, you are getting it exactly 6. Then trapezoid is Simpson also with the same number, 0 errors. Because the function is a straight line to x plus 1. And this is what the area under this curve. X square is parabolic. Well, this is also giving an exact value for 48 case of the trapezoid is an error. This Simpson is almost reached to the given 7 or 8 accuracy, you have an 0 error. Midpoint, yes, you do have some finite error. Okay, this is error huge, in fact, at the 48 iteration, which means I cannot really afford to do this kind of midpoint or a right sum or left sum. Midpoint is also have an error, it's better than compared to other. There is an error compared to Simpson. Right sum, left sum. Okay. Go to the e power a 2x, which we have seen enough. This is 1/3. X power 1/3. 5 times x power 1/3. Let's see here what the Simpson, even Simpson. Okay. You could get the idea now.
Yes, sir.
You can see here, even 40 steps Simpson, the error is 10 to the minus 2. And now you will appreciate that, yes, one should be very careful about it. Depending on the function, one should carefully select the method and use it. Okay, let us try to see what is happening for the party of that. Left sum is 10 to the minus 1, right sum is 10 to the minus 1. The point is better than the Simpson even. Is it right? Yeah. Okay. You follow what I'm trying to describe here. But this Simpson error is much higher when compared to the midpoint. 1 order is more. So this seems to be much better when compared to the Simpson. But the function of cube third root of x power 1/3 5 times is much better. And what about trapezoid? That's also bad. So midpoint seems to be better. So seems that will be, this is supposed to be used and compared to all the other 5 methods for this function. Then now we have a x divided by x squared plus 1. Okay, we start from left sum. 40 points, 10 to the minus 2 seems to be okay. It's not too good. It's also our same order, and the left and right is almost similar, which will vary only this the decimal part of this. How much is the difference? About 0.02 is the difference. Yes. Midpoint. Oh, not bad. See? 10 to the minus 5, where we have shifted from 10 to the minus 3 orders has been jumped. The midpoint. Okay. Trapezoidal, we have again 10 to the minus 5. So midpoint and trapezoid seems to be competing each other, as I said. This is going to be much better. So smooth continuous variation is there, then this function is better. But when it comes to the variations like what is happening here, at the initial value it is very slow. Okay, then it's going to almost straight line path. Then this contribution of error in this region seems to be much higher than compared to this region what you have. So exact area and this area, this is the error. And what about here? Midpoint sum is better. Right, so this side is also around that. No, the midpoint is better. 9.45457 approximate area. This is the exact number. So this is about 10 power minus 3. Okay, so it's so clear that we have to really look for what? Nature of the function first, integrand, how does it behave? Okay, and then you have to pick out the method. So this is how we'll be looking at things. We can see this function. No, I don't have this. This is another complicated function. You can, this is for, is it Simpson method? 4 times and then the 2 times. Yes, this is the magnitude of the error, and the function what you have here. Well, I think this is the function. Plot this as a function of x, then that will give an idea. Plot as a function of x, that we take 0 to 8 or so. And say, oh, something very difficult for you to try with this. 3. I'll reduce the region further. 2. Or maybe this, you can see that this is how it's going, and you have to find the area. If I go to the higher range of region, then you have to be careful about the analysis and number of points. I believe that this meant for this Simpson rule only. For the number of points is given numerically 18 and 1. This is the numbers that you have. And what is the range is given? A and B is what? 0 to 1.5. So this is the range for which this function is being evaluated from here 0 to 1.5 area under this curve. That is being calculated. For the number 1 iteration, this is the number. If it is 18, 6 points, so now you can see the difference. Suppose if I make this is the just number we are getting directly. Suppose if I make like 50, 6.69. Then go to 150. Yeah, we are almost saturated now. Say maybe even 50 itself we have reached that number. And if I try here 40 again, we may end up with the same number here. Yes, 20, 6.69. So 25. By having 25 points, we have reached this number, which is going to be same. And that can be. So this is the area under the curve for this function, the region 0 to 1.5. And actually, what is the area which we refer is filling. What do you do? Filling at the bottom. This is what the area which we have calculated. That's the number. Okay. So now this n varies, and you can make a plot and see how the numbers are varying. And that's what you are visually seeing. You get the point? The number of points what you are trying to vary here, which gives the number. That number variation can be directly given, and you put the function, actual function, and then find out for given n how the error is changing. That also can be found automatically. It's possible to do that. So you make a small program. For each method, you try to write a program which will help you to learn the Mathematica code, for developing a Mathematica code on your own for each one of them. Okay. Then make a plot of these boxes on your own, because you will think about what is to be done for making the boxes, which I have described here by getting the points. The previous one, what I have shown, no? You see, delta x is not. This is the actual this is over. Integration is done. So for the given number of n, this is done, and you know the actual value difference. You don't have to do anything further. But what is important is, if you wanted to have understanding of these things, then you have to really make an effort to see that these points may be used to make such graphs, then visualize it, then vary the parameter and see, and try this for, now as I said, already it's available for you now. Okay, copy and paste, and change the initial part of this, this alone you change it. Xi star alone you change it. This is same. For the left sum already I have done. For the right you do this. Xi star equal to Xi itself. For the middle you do this one. Then you would see these plots will be generated automatically. And then change the number of points and do that. And same thing you extend it by taking this also. That's what is being built here. You can do it one by one. Don't have to put all of them together, because that requires a lot of effort. But we can do one by one. Do it for 2 or 3, or you can try with right sum and trapezoid. You try and make sure that you are able to produce it. You're able to see visually that what is that integration is going on, and calculate this such as this error, put it in the box, exact and approximate error, all can be put into this, and then make sure that it can be used. Nothing great, it's all available here also. You can, when you go through them, you can understand what that has been done systematically. This is again initially is getting all in the form of a points, and those points he has been explored them, putting in this form. That's what the idea here. Okay, so and which this gives a much more deeper understanding of what is that we are trying to do. Okay, so these are all so-called applied mathematics, where people try to explore them. Okay, they study detailed way about this errors and error analysis. Okay, numerical techniques for various methods. Then they go for the special function and see. Then they will also describe for each one of the integrand what could be the nature of the behavior of the functions for a different values of the points and different methods. They provide all information. There are journals which is available. Right? If I am right, I have one of the math paper integration. Yeah, you can see here. Okay, numerical integration of periodic function. You have a few examples when this is published. American Mathematical Monthly. Okay, and this is nothing but the paper, whole paper contains all the things which we are trying to describe for understanding this numerical integration. About 26, how many pages? About 26-page article. So whatever she described, there are journals, they are available, and there is every stage there is an improvement about it. People provide all possible informations that are required for this functions in a deeper manner. So all related to this methods that are given, about 36-page article is given here, and this is published here only on the numerical integration of a periodic function. Okay. In fact, these are all one of the more popular calculus textbooks problem has been taken, systematically done, then selects various methods. So some preliminaries have been described, and there are various functions because all possible periodic function is taken. Okay. Convergence rate. So what is the rate of convergence? And then he has given some sections where it is being described. If it is a complex function, how do you do it? So these are all actually the applied mathematics people try to do. But we are not interested to give some extra things here, but we want to understand them and use it for our computation wherever we require. Okay, that's the idea here. Or if you want to shift over to applied mathematics, then you can think about trying to do some such work. Now, because of Mathematica, things are to be much easier. You can really predict everything with the numbers and formulate the theorem based on the number that you are going to get. Super geometric convergence. E power a cos x between 0 to 2 pi. Interesting functions. Again, sub-geometric convergence. Okay, e power of cos x minus 1 divided by cos x plus 1, and same region. So like this, these are available, and you master some techniques like this, you can go ahead with thinking about some particular group of functions and try to provide as much information as possible. These are some of the references that are available, and the fellows already done nice piece of work on this complex error function also. Same fellow, this is the author. And some description about the authors. So I think there are very many methods. A lot of things has been available on this numerical method itself. The small articles like this, that their understanding has been published, and we try to use them for our numerical techniques to solve the typical problems where you need to have the numerical techniques. Okay, so I hope there is clarity in your numerical integration by now. And you can think about other methods by using the Legendre polynomial, not Legendre. Gaussian quadrature. I do not know whether Gaussian quadrature. You have done that? You have that in your syllabus?
Yeah, we have already done it, and
Gaussian quadrature, is it?
Yeah.
Oh, that I think
That
I have.
basically translating the function between a to b to 0 to 1.
Yes.
Minus half to plus half.
That's right, like. Precisely. That's right. And then you need to use the roots of the Legendre.
Yeah.
That roots will be going into the calculation, is it not?
Yes, sir.
Area summations. And I think I have did long back. It must be there. That program is available in the Mathematica also. Maybe in the next class I have to see my disk now somewhere. I have to pick it out now, because Gaussian quadrature I did it, and then two more methods also I have added. Not only 0 to 1 conversion. There's two more methods are there. You can go to 0 to infinity also. No, minus infinity to plus infinity integration by using a Hermite. Okay, Hermite can accommodate from minus infinity to plus infinity. Right? That also can be used. And then one more also. I think 2-3 methods which I did long back. I think my disk it will be there somewhere. Probably if I can get it, I'll show you. At least I just show you that how that is being done using this. Because root finding will be much easier, because there you will take the root from the standard integrals. Or
okay.
You have the standards, Mathematica standard, this thing, tables. Am I right? You use the tables. Oh, that's out again. My net is failed. Yeah, it is disconnecting.
Yeah, but we could see your face and
yeah. But there is a red light comes and goes. That's why I'm not able to. Yeah, that's right. Yeah, that's right. So what I will do, I'll just pick out those methods also. Maybe I'll just show you how it is being done, and then we will learn little more on that. Let's not spend much time on that, and then we will go to the. Is it enough for numerical methods for the integrations?
Yeah, really. Because we greatly got the understanding about the left sum, right sum, that is.
Yeah, that's right. That's the base, and you can really get an idea about how the error comes, and how the error varies from when you go for a different function. So that also is an idea. Yes, that's right. That's the most useful thing, and also good feel for numerical integrations. Okay, that's good. So maybe I can stop here now. So we'll meet on Monday. Around 2:30. Yeah, right. Bye. Yeah, I'll send it. Yes. Right. Bye. 8 o'clock session. Yes. I hope there may be some guest. I'll just find out, and I'll inform you, because there is some. Yeah. There is some guests have come. I just check it now. Depending on their stay, I'll just decide. Okay. Right. Okay. Fine. Bye. See you.
Have a nice weekend.
Thank you. Sorry.
Okay, we will stop the class now. Thank you all.
Thank you, sir. See you in the next class. Bye.
Thank you, sir.